Hello and welcome to my presentation on current driven MHD. My name is SWAPNIL and I am a PhD student at IIT Bombay, India. You might have studied right hand thumb rule, in which the direction of the current in the thumb direction induces a magnetic field in the direction of curling of the fingers. The similar concept we can also use for the point injection current in the liquid metal electrode pool. So the current when enters from a concentrated area diverges into the liquid metal pool, and when this diverging current induces a magnetic field and interacts it's with own magnetic field, produces a Lorentz force. That Lorentz force is generally non-conservative and drives a flow inside the liquid metal pool, which is known as the electrovertex flow. So this electrovertex flow finds its application in many devices, and one such device is the liquid metal battery for the grid scale energy storage applications. So here you can see the schematic of the LMB, which has multiple layers and different conductivities. And you can see that the current enters from a concentrated area and diverges into the different layers. Because of the different conductivities, seemingly simple concept has lots of complexities. And on the rightmost figure shows the experimental setup used in the literature. So to reduce the complexity, we use only the single liquid metal electrode layer. And the right bottom animation shows the electrolytic flow evolution in the top electrode of the liquid metal battery. Since I have mentioned that the electrolytic flow depends on the applied current and its induced magnetic field, and the induced magnetic field can also be calculated with the three approaches. So in our present study, we evaluate those three approaches based on their speed and accuracy in a single liquid metal electrode layer. So these are the three computational approaches. Out of these, the first one uses the Biot-Savart law, in which the magnetic field can be calculated with the help of complex integral. And you can see that the integral has cross product also. So this is computationally intensive. Upon simplification, we can get the field because of the long current carrying wire. But to avoid the complexity, alternatively, we can use the second approach, in which we introduce a vector potential. And by taking the curl of that vector potential, we can get the field of the field inside the liquid domain. But alternatively, you can see that there is an additional step associated with this, and it can introduce the discretization errors in the numerical computations. In the third approach, we altogether omit the complex integrals and the cross products. We use only the Poisson's equation for the vector potential relating the scalar electric potential. And thence we can reduce the complexity. But the third approach depends on the externally applied boundary conditions of the vector potential A0. So in the literature, all the three approaches have been used without any clarity on their merits and demerits. So we explore these approaches for the simulations. These are the governing equations. The Navier-Stokes equation has the Lorentz force term as the driving force. Here, the current density can be calculated with the help of equation 4, which is nothing but the Ohm's law in another form. And here we have assumed that the current density is divergence free. So in the first approach, to reduce the complexity, we use the complex integral only at the domain boundaries and solve the Laplacian equation of B to get its interior value, which is suggested in the literature. Or alternatively, we can use the similar approach for the vector potential, and we get its value only at the domain boundaries. And thereafter, we solve the Poisson's equation to reduce the computation time. But along with the B, we also assume here that the A is also solenoidal in nature. In the third approach, as I have discussed, it is the Poisson's equation of vector potential, and it depends on the externally applied boundary conditions. So in our study, we found that, or we have several questions that do these approaches give the same magnetic field and the same electrovertex flow evolution in the domain, or the approach 2 or approach 3 can be used for the simulation of electrovertex flow? So these questions motivate our study. Since I mentioned that it depends on the boundary conditions of anode, so these are the boundary conditions which we use at the domain boundaries. We also explore the boundary condition of electric potential, but I'm not presenting this work here today. Uh, Another boundary conditions for current density and magnetic field, since these boundary conditions are overwritten, so no matter what boundary condition we apply, it will be overwritten. And we usually use no-slip boundary condition for the velocity. So this is the solver which we developed to simulate current-driven MHD flows in the single liquid metal electrode layer. And we have applied the pimple type corrector loops for the electromagnetic variables as well. And those corrector loops helps to reduce the continuity errors in the domain. On the basis of MHD form, which is fictitious magnetic pressure for the magnetic field, we propose a fictitious pressure for the vector potential to solve its transport equation, especially for the later two approaches in our simulations. So we use Zillion's test case, which is complex in nature, which is solid liquid coupling. But to avoid the complexity and to get started with, we use only the liquid domain, which is shown in blue color, to validate our solver. And we assume that we have fairly good enough relation, so we proceed with that. These are the geometry details of our study, and it has the aspect ratio of 2 with the diameter ratio of 1.2. We use the three different meshes, and these are the grid independent results at two different line locations in the domain, one in the z direction or one in the axial direction, and the second in the lateral dimension to the flow. So based on this, we choose almost 12,49,500 cells for the computations. We use these constant parameters for the study. We use only 200 ampere current in our study. We apply it with the help of fixed gradient of electric potential boundary condition at the concentrated current collector, which is blue in color. In the current-driven MHD, the relative strength of electromagnetic and viscous forces is denoted by or presented by a non-dimensional parameter known as the EBF parameter. Here, its value is quite high, so it drives a flow, it overcomes the viscous forces, and that's how we get the flow inside the domain. These are the properties of the liquid mercury. We have also explored the numerical schemes, two sets of numerical schemes, but I'm presenting the results only for the S2 schemes, which is the fourth order gradient scheme with cubic interpolation. So these are the magnetic field contour plots in the top row obtained with our 3D simulations with the three approaches. We can see that there is a clear division, or we get relatively higher magnitude of magnetic field with the A2 and A3. Consequently, the bottom row shows the Lorentz force distribution, and they are in correspondence with the magnetic field. So with this, we expect that we expect the higher EVF intensity with the later two approaches in our case. As I have mentioned that we have only assumed the electromagnetic quantities as divergence free, which are current density, magnetic field, and vector potential. But we have observed that this is not the case, and they are not divergence free in the computations. So we quantify those errors with the help of some local normalized error formula, which is given in the slide, and we quantify the errors with this formula. Based on the complexity, we have observed that the computation time of magnetic field with approach 1 is almost higher, which is 224.2 seconds compared to the approach 2, which is only 30 seconds. So it was speculated that approach 1 is slower. But in our study, we have observed that total computation time, which is shown with this bar chart, with these two approaches is quite high, and it is almost 80 hours plus compared to the A1. So if I talk about the errors in the magnetic field, which is given by the mid plot, and here you can see that the bar with the orange color shows the errors without the introduction of the corrector loops. So with the help of introduction of corrector loops, we could reduce the errors almost by 85% in A1. We also see that there is reduction in errors in B0 with A2 and as well, but there is a catch here. To study these approaches for to study these errors for the later two cases or later two approaches, we should not look only for the div B error. we should also look for the div A error, because by definition, the vector potential satisfies the divergence of B. So why this is so? This is because of the finite domain size which we are using. And the equations for approach 2 and approach 3 are only valid for very, very long domain. So this violates the law. But before coming to final conclusion, we would like to see the electrovertex flow evolution in the domain. So we had questioned that do we get the same magnetic field? So it was nullified. It was quite contradictory in nature. Similarly, here we see that the flow obtained with the three approaches differs quite very high. We plot the axial velocity uh, along the z direction and again in the lateral direction. So here there is a clear division. Again, we see that the red line plot is in correspondence is in almost equal to the nearly equal to the validation results or reference results. However, approach 2 and approach 3, which are yellow and green in color, or over predict the velocity. And that's how we need to cut down or we need to reduce the time step. Thereby, we are getting the higher total computation time with these two approaches. So in our study, we found that the approach one is not only faster but accurate as well. So these are the summary. We have evaluated three different approaches to compute electrovertex flow in our study. And we find that approach one with biosubvert law is the most suitable approach. I leave you with the conclusion, which I have directly or indirectly discussed in my presentation. So this is a part of the work which we have recently submitted to JCP. And this is the ongoing work which we have added the Joule heating term, buoyancy term in our solver as well. We are also working on the simulation of multi-layer liquid metal electrode batteries and solve the coupled electromagnetic equations in the domain. We would like to acknowledge these persons and thank you for your attention.
Any question from the audience? Well, that's the first time. Relation stable, so we just did it for applying so you have maybe a divergence, maybe you have to do some kind of workaround to approach the problem. So we check. I mean, the question is, we see the process of each other. That's true. And any problem has some information on the state. Like that, the state
not really. We found the magnetic field quite high, but the pattern was similar. We don't find any violation with the pattern of the magnetic field and the flow. But what happens is here, because of the higher velocity, we get this down pattern, which is non-physical, almost non-physical. But this is the outcome of the study. If I talk about the simulations, so all the simulations are conversed. And this took almost 15 to 20 days to run the simulations on the 16 processor. So as far as simulations are concerned, we don't see any pitfalls.
He will present us the way he simulated cells and then providers. Is spoken by the way. So please.
Thank you. So today I would like to introduce a few two projects. So this framework implemented into OpenFOAM, and it is a new computational tool for fuel cells, electrolyzers, and other electrochemical devices. First, I want to it's stuck. Now we get somewhere. I want to say that I think 2 weeks ago, we submitted our paper and a preprint to a journal, which can be seen on the right. And on the left, more importantly, are the collaborators and corresponding authors. So maybe start with them. So this would be Steffen Beal and Shidong Sam. So he was a PhD student in the 1914 in OpenFOAM, and he started kind of this development of this Open Fuel Cell 2 project. And additional authors I want to mention here are Holger Marscher from the TU Darmstadt, Uwe Reimer, Werner Lehnert, and my person from the Forschungsinstitute. I also want to say here that the code maintenance, development, and further improvements are basically done by postdocs. So this would be Shidong Sang and me as a PhD. So, and this brings me directly to my agenda. It's pretty straightforward. So I think in our community, the topic of electrolyzers and fuel cells is not that common. Because of this, I want to give a short introduction about that. And then I want to go directly into the solver itself, and want to say what's next, what comes next, etc., and where you can apply for the code and get the code and run it by yourself, if you like to. So let me start with this. When we have a look at electrolyzers or fuel cells, there's a huge range of scales which can be considered. So when we have a look at the left, we can start to describe the whole system of the fuel cells or electrolyzers, and we can go down by scales. So we can go down over stacks and to single cells, and even into porous media. Like we want to describe the two-phase flow within those porous structures, or even smaller when we want to describe the electrokinetics on the electrodes. What I want to talk about and what the Open Fuel Cell project is all about is the cell modeling. So this is our scale we are working with. So we want to know what happens within a single cell. And with this, a very basic introduction, and I will keep it short. There are mainly two counterparts. So those are fuel cells and electrolyzers. So for fuel cells, as can be seen on the left side, we have to put in chemical energy, like our species, hydrogen or oxygen, to generate our power to run our device. And vice versa, then when we are considering electrolyzers, we have to put in power to get out what we want. And for example, for PEM electrolyzer, this would be especially the hydrogen. What I want to mention here is, despite the different functionalities and different chemical reactions, we have a kind of similar structure. And the point is here, how can we exploit this? How can we put all of this together with the physics into a CFD model? So when we have a look at the cell, here, for example, the PEM electrolyzer cell, from the outer to the inner, we have different components, beginning with the outer end plates, which holds everything together, and then going in and considering bipolar plates or monopolar plates, whatever you are thinking of, like. And in between, you get these functional layers. So you have different porous media, depending on the cell you are considering. And within all of this, there is a membrane. So now the question is, as I said, how can we put all of this into one code? And there I want to give an overview, because we call the solver or framework of Open Fuel Cell 2. So there has to be an Open Fuel Cell 1. And this was called Open Fuel Cell, or this project was called Open Fuel Cell, or is called, because it's still existing. And this one was initialized by Steffen Beal and Hor Piasak back then. And it was basically the first open source solid oxide fuel cell code out there. The characteristic of this code was it was single phase, because they considered a solid oxide fuel cell. And the chemical reaction takes place on an infinite thin surface. This will become important later. But nevertheless, because it's Open Fuel Cell 2, we took a lot of classes, a lot of structure from the code to improve it and change a lot to create Open Fuel Cell 2. And to explain the methodology of this framework, I want you to consider a single cell, a really simple single cell. What we can do now is we can split this up into different regions. We can solve within those regions for different kinds of sets of equations and closures. So, for example, when we're considering the fluid regions, we want to calculate for the fluid flow. This is We want to solve the speed transfer, the two-phase flow, which is done in this framework by an nonlinear approach, and the electrochemical reaction plus the heat transfer. Coming to another region would be the electric region, called in this way, because there we are solving for the ionic and electric potentials. And when we're considering a PEM fuse electrolyzer, the dissolved water content within the membrane. What I want to mention here are some assumptions, which I think are important to know. So first of all the simulations we are doing in steady state. And when we are considering two-phase flow, we apply for a local time stepping scheme in order to stabilize the overall solution process. And what's important here, the electrochemistry or the reaction takes place on a volumetric region, which are the electrodes, and we do not resolve the interface between the phases. So it's a microhomogeneous approach. For now, this might change. So what's the methodology of our approach? So we're exploiting, among others, the class called region type. So with this, we can consider those different regions. And on each region, as I said, we are solving for different equations. Here, for example, electric potential fields, etc. But what I want to stress here is the fluid region, because here it becomes a little bit more interesting, because we are able, or we want to have information about the two-phase system within those cells. So we apply phase system, and the user can choose between a single-phase system or a two-phase system. And within a two-phase system, you have two phases. And these phases, based on the phase model class, this means you can give them also properties. So you can say what's actually solved within those phases. And then, of course, those are distinct governing equations which are solved, but they are interdependent, so they need to be coupled. So there are mainly two strands. So we need to couple the fluid region with the electric region, most likely due to electrochemistry purposes. And what we do, we collect all the data for, let's say, heat conductivity, etc., from all of those regions, mapping this to the main region and solve there for the second temperature equation or enthalpy equation. I want to shortly give you a short introduction about the governing equation which has to be solved. I don't want to go into detail here, but when we are in the first meter, for example, we have actually three phases to consider. This is the solid phase and the two liquid phases, two fluid phases, which can be gas or liquid. And so we need to apply conditional volume averaging to derive our governing equations. And as I said, when we are doing this and when we have a look at the momentum equation, we have those coupling terms. This is the momentum interchangeability, so it's MQ. We have the Darcy resistance term. And what we also can't neglect here is the capillary pressure. So we are in the porous medium and we have different contact angles, etc. So we need to collect them. What I want to stress is that we are solving for one pressure. So we form the sum of the mixture of the continuity equations to derive our pressure equations, right? So liquid and gas phase share pressure. Here also the other equations. Here I want to mention on the right side you see those source terms, beginning with the mass transfer term, coming from the electrochemical reactions. So we want to know locally where are the species located, hydrogen, oxygen, and water. The same with the heat transfer. Important here, the source term. I want to mention due to the reactions and overpotentials, etc. You have waste heat which goes into the system, which has to be considered, especially for fuses as electrolyzers. And on the bottom, when we have a two-phase system, they're interacting with each other. So you need a mass flux between the non-resolved interface and the heat flux. That is very interesting to see some different equations. How do we describe our electrokinetics? We are doing this by applying a Butler-Volmer equation or Tartan equation. Together with Kirchhoff and the Nernst potential, we are able to close the system. So we are able, in the end, to solve for the two potentials we are solving for, because from the Butter-Bohm equation we get a function between the current density and overpotential, and with this we are able to simulate the potentials. Nevertheless, maybe coming now to an interesting part. What is actually the code capable of? So what I will show you later is like a web page where also those tutorials are shown, or which will be set up in some weeks. We are a little bit delayed. So what you can see here and what you can calculate when we're considering a low temperature PEM fuel cell. When we start at the bottom, at the top left, you can solve for the dissolved water content, as seen here for different current density applied. On the bottom left, when you're interested in the gas velocities in the channels, or even in the concentrations in the electrodes, in the porous media, etc. That's not only local values of what we get, it's also on a macro scale, I would call it this way, very important data are polarization curves. Like they characterize the system, also see that this much it delivers, etc. Of course, PEM fuel cell is not the only thing you can calculate with this. I choose this simple case as intentionally because it shows what's actually the code is capable of. What I want to show here is a PEM electrolyzer case, so same geometry, right? But different functionalities. Here I want to stress out that we are now producing gas in a liquid environment. So what you can see here on the top, less water is created at the anode side in comparison to the cathode side. This is reasonable because when you have a look at the reactions for each electron transferred, the double amount of hydrogen is produced in comparison to oxygen. And I'm finally close to the end. So we want to publish our code. And the code actually has tutorials in this, and the user can decide what he or she wants to simulate. This is that the code is currently applicable for low temperature PEM fuel and electrolyzer case, high temperature fuel and electrolyzer case, and also solid oxide fuel and solid oxide electrolyzers. When you go to this page, you will find workplace under construction. So, but this will turn up, I think, I hope, after the invitation. So when you go to this page, this is why I wanted to open this. Is it still shared the monitor? Yeah. Share again. Yep. All right, should be fine, right? Yeah. So when you go to this web page, might for some people look like similar. They have seen this already, for example, Solid for Foam, so shout out for them. Or I think you also has this overlay. I'm not sure about this, but what you will find here is when you go through it, how to install it. Well, at first, maybe how to get the code. So there will be a GitHub repository. And then when you have here a list of all the tutorials, so there will be a description of how to run this, right? So you can do it by your own, and you can also go into the source code and do whatever you want basically with this. And stop sharing, right? Stop, right? Your presentation. Yeah, right. Sorry for the convenience. Maybe stop first. 15. Sorry. I should go forward. Maybe just stop and go in again. Okay. And with this, let me It's a different one. Yeah. Oh, wait, this is the PowerPoint, right? Okay. We are on? Okay, I'm sorry for this, and maybe it was not worth it, because now I will come to an end. So, in general, we want to transfer from our private GitLab repository all the stuff into a public GitHub repository. I think you will. So all of those who are interested in this, you will notice this when we publish this. You will definitely. And there are, of course, also some new ideas what we are working on now. So, for example, alkaline electrolyzers, introducing also Nernst Planck framework for this, and also improved numerics. So improving region-to-region coupling, for example, which is a big deal via region block coupling, etc. So with this, I want to say thank you and ask a question if you like to. Thank you. Thank you.
Any questions for the audience? My question is that you have not solved business already. Okay, so there is a question.
Yes, there's no question solved in the solid. I didn't want to tell it here because it leads to some confusions. That's definitely actually reasonable because we have two systems. We can choose a single-phase system or two-phase system. And we map all the data back to a main mesh where we solve the temperature equation. When we consider only one single phase, we only have to solve for one temperature, right? And this is not done within solid regions, rather than in the main region. When we are considering a two-phase flow, we have two enthalpy equations for each phase. One is solved in the fluid region, and the other one is solved on the main mesh. So every data is mapped to a main mesh, and this is like the same temperature for the second phase. I didn't get this, sorry.
So the Excel is something like internal Excel. It's like some creative part of the solid, preparing part of the solid internal Excel. You can do this full cell code. Yeah, so what lies the problem is that something with radical particle is related to the neutron mixing. There is a square law and there is a full law. So some particles are being bad something else. My job is to cause out the radical transfer.
This goes also in the direction that they have this solved materials from the solid into the you can try. This idea, I would say, it's not new. I got this question already. So just if you're able to do this, yes. It's not complicated like that. This is what I want to say. Definitely, yeah. And this is not a simple question, simple task to do everything. It's long, yes. It's your turn.
For the embassy question, our formats are piece, and then you pick out based on various measures, but they don't belong to each other. They actually have a lot. Would you have a hierarchy of measures to map up the master mesh, or are you using GPI?
This is cell cell mapping for now. What I wrote at the last thing, we are about to improving this, so that we get rid of the main mesh, because this is in this, right? This is not because we duplicate data, which what we actually do not want. That,
In different ways of what you do, so
Right.
somebody what kind of thing.
yeah, that's true, but it goes into the direction of we are gluing every matrices together. Exactly. An instance of this and a variant of this, yes.
You can start it, so it's not, you can keep a start the whole first. Sorry, because the microphone is far from me. Please start your presentation.
Okay.
Thank you.
Representing a modified overhead network of a form for simultaneous motion and information with supervision of Karim Ahmed and Professor Forth and Professor Chatelier. The outline of this presentation starts with motivation, then the introduction will be presented. Next, we will discuss our objective in this study, then a model description are stated, and we will discuss our results and discussion to finalize with a conclusion. Due to the growing need for the aviation and the maritime industries for biomimetic technology during the past 20 years, many researchers have concentrated on simulating such complex biosystems. One fascinating phenomena is the field of animal propulsion and mobility is the wing flapping action. In our study, we will focus on the oscillating foil-based hydroelastic energy harvesters. Simply, this concept is based on the self-sustained flapping motion of the foil, also known as flutter motion, due to polypassive flow-induced instability. This flutter motion is generally a combination of pitching motion and heaving motion. To perform this simulation, we will need to have a numerical tool capable of achieving the required motion. Dynamic mesh motion for flapping motion is a bit complex. The complexity of the flapping motion lies in the combination of multiple motions, rotation, and heaving. Any solid body motion such as heaving or deformation with a small amplitude can be achieved with deformable moving mesh that follows the arbitrary Lagrange variant technique. However, using the deformable moving mesh to achieve both rotation and heaving motion will squeeze the mesh cells, increasing the non-orthogonality in the case of small rotation motions and numerical failure in a large rotation angles and large translation motion. Thus, our objective is to introduce an interesting mesh motion approach, which is OVERSET, illustrate our tuned solver in OpenFOAM that enhances the actual OVERSET to meet our requirement, and provide it from using the new solver to improve its functionality in achieving the required mesh motion and information. OVERSET grid technique is generally based on generating sets of discontinued component meshes. This discontinued meshes cover the whole domain and overlap at the region of the motion, and the component of mesh can be either structured or non-structured. At each time step of the solution, the cell in the front and the background mesh will follow one following types shown in the figure. The first type is the calculated cells, for which covering equations are solved. The second is the interpolated cell, whose value are interpolated from the neighbor cells of the other mesh. The third type is called the holes, for which cells are removed and no solution is evaluated. The working principle is solving the governing equation in the discontinued and front mesh can be summarized as follows. When we are solving inside the background domain, the mesh elements related to the front domain are treated as false and excluded from the computational domain. The boundary value of the OVERSET domain, the boundary of the front mesh, is then interpreted to the background mesh. Within the front mesh, the same procedure is performed. Our targeted problem is to achieve combined simultaneous rigid body motion and deformation. The rigid body motion follows the flapping, which contains heaving motion, sinusoidal heaving motion, and sinusoidal pitching motion. Heaving means that we move up and down. Pitching, we are rotating our airfoil. And with the deformation, we are achieving a certain kind of deformation for the leading part and the trailing edge part, as shown in the figure. The current overset model in OpenFOAM, this is the sinusoidal motion, can be easily done in OpenFOAM. Sinusoidal heaving and pitching without deformation, and also a deformation also done in OpenFOAM. So in the working methodology here that's available in OpenFOAM right now, we have a steady background and solid body motion like the video right now. But the desire is we want to achieve a deformation for the foil batch. This will deform the cells in the front mesh and keep the background mesh fixed. But however, when we try to combine these two kinds of motions, the rigid body and deformation, the solid body motion happens for both front and background mesh. And this is not the case that we are seeking for. When the default overset solver applies the solid body deformation, it can separate the mesh into different zones, applying the motion to the front mesh and keep the background mesh stationary, as you can see, as the blue and the red colors. However, when it comes to applying a batch deformation, the solver fails to distinguish between different solvers and it treats the whole mesh now as a single zone, the blue color, losing its affinity. So we have a dynamic overset FV mesh in the library structure of OpenFOAM currently, and it's containing a certain motion solver. We will copy this motion solver and inspect it. By inspecting it, we define that the dynamic overset FV mesh is depending on the dynamic FV mesh. And the dynamic FV mesh containing different motion solvers. But the one that's used in OVERSET is called dynamic motion solver less. It will be motion. And by comparing between the available different available libraries in dynamic FV mesh, we can find that the last one doesn't have any zone ID, which is the parameter that define different zones. However, the multi motion solver having the zone ID that can be used to define different zones. So our target is to edit our motion solver by copying the dynamic multi-motion solver and use it in the dynamic overset FV mesh. And by doing this, we take this edited motion solver and add it in a new dynamic overset zone FV mesh. Why we are naming a new subroutine? We are naming a new subroutine to reserve the old one, and we can use it for comparison later on. And here, this is our result of success. You can see the deformation and the flapping from the foil is achieving very obviously for the front mesh and keeping the background mesh as stationary. And we also applied to another problem. Here we consider an air bubble affected by a acoustic wave, another case to show the diversity of applications that can be used for that. The results are presented to test the functionality of the new solver in solving the flow while performing the deformation required at both front and background mesh. The velocity and pressure field show smooth transition of the solution from background to the front mesh and vice versa. And there is the orthogonality lies right now. So our conclusion is fault overhead solver we mesh has it to be dynamic overset we mesh, which is capable of applying rigid body motion and deformation at the select batches in the certain zones. But it can also provide a stable solution. The presented wall can be cornerstone for many problems in the field of flow destruction and action, which may have been impossible to achieve so far. It didn't require a lot of hard coding. It required understanding of how the overset was working and where was the problem. Then go deeper inside the code workflow to reach the point where we can add our application. Our future work is to build a complete FSI and numerical tool by coupling the OpenFOAM node solver with any solid solver. And recently we managed to achieve some steps towards this. This is the reference that we used in our work. And thank you for your attention. If you have any information, don't hesitate to ask us in the Q&A or contact us through the emails. Thank you again.
Yes. Hello?
Question over there? Yeah.
I'm sorry, I didn't hear the question. If
Hi, thanks for the talk. I would like to know if, in your experience, is there any possibility to introduce a deformation in the background mesh as well? So not only a rigid deformation in the background, but deformation and motion, rigid motion and deformation also in the background mesh.
Yes, this is what happened when we tried when using OpenFOAM itself. The deformation happened in both meshes, the front and back. The front and back, but we wanted to keep the back fixed. There is no deformation in it, and only deform the front mesh. As you can see, this is like the back one is moving with the front, and we wanted to keep the background fixed and only deform the front, because the full problem is not having the airfoil flapping. There is like multiple objects that need to be moved, and if the background moves with each body, this will not mimic the condition that we are seeking.
I understand. Of course, in your case, it makes sense. But theoretically, there is no problematic to introduce a deformation also in the background mesh.
No. But I mean, if in the case that we have multiple bodies,
Okay, yes.
this is we need to make the background fix it.
Understood. Thanks a lot.
Thank you.
Yeah.
Let's take another question. I have a question. It's the last one. Second. What about validation of this approach? So have you done a rigorous validation, or you're still?
Yes, right now we are validating with our solver with in a float problem. The one of the reference. Let me show you the reference that we get this equation from. We are trying to calculate, do the simulation. The simulation is running right now, and once it's fully established and we have the result, we will publish it in a journal. So we are going to, but for the meshing side, we believe that it's meeting the requirements because we achieved to conduct our motion.
Okay, that's good. Thank you very much. So any other question? The session is closed now, and everyone enjoy the evening in Genoa. I thank you for